So let's have a look at probability distribution. So this is just a particular way of representing probabilities where the probabilities are not equal. And in this case, it's discrete. You can see that x is a fixed integer, either 1, 3, 5, or 7, and that it has an associated percentage probability below it. So what this says is that the chance of x, an event giving the value of 1, has a probability of a fifth. And we can write that using this, meaning that the probability of event x, where x, big X is equal to little x, is listed here. So that means the probability of getting a 3 is a tenth. Probability of getting a 7 is 2 out of 5th. Now, the first thing that we can do is we can actually verify that this is a reasonable probability distribution. The first thing we can do is just look that this all adds up to 1. Why? Because the probabilities should always add up to 1 if you have every single probability. We can see that that's 2 tenths plus a tenth plus 3 tenths plus 4 tenths, and that does indeed equal 10 tenths, which is 1. Alrighty, so this is indeed a probability distribution. It's a fair one, and now we've answered the question. Alrighty, so whenever you're given one of these distribution tables, a good thing to think about is, does the probabilities of the bottom row actually equal 1? And if they don't, then you know that something has gone wrong in that table. But this is a fact we can play with. So in this probability table, you can see that there's actually a variable missing. We've got a k on the bottom. Well, since we know that all of these added up together should equal 1, we can use that to actually solve for k. So 0.14 plus k plus 0.36 plus 0.21 should be equal to 1. Right? When you add up all the probabilities, sum of all probabilities should add up to 1. Alright, so let's tally up these probabilities. These first two add up to 0.5, 0.71, 0.84. So the next line is going to be k plus 0.84 is equal to 1. Subtract 0.84 from both sides, and we are left with 0.16. So k must be equal to k 0.16. Alrighty, and this is just a slightly more complicated one. We've got k, k on 2, k on 3, and k on 4, 0.25, and we're looking for k. Now, same rule is going to apply. The algebra is just going to be a little bit more tricky. So let's write it all out. K plus k on 2 plus k on 3 plus k on 4 plus 0.25 equals 1. Now in this case, I've already got the 0.25 by itself, so I can subtract that to the other side and be left with 0.75. For the left-hand side, every single one of these has got a different denominator. Denominator of 1, 2, 3, and 4. So how can I most easily get them to have the same base? Well, 4 and 2 share a common factor, and the lowest common denominator between 3 and 4 would be 12. So let's make these all written as 12ths. So 12 twelfths. K on 2 to look like 12 times by 6, so 6k on 12. 3 to make look like 12 times by 4. 4k on 12. And 4 times by 3, so we can get 3k on 12 equals 0.75. And now we can just add up all of these numerators. We can have 12 plus 6 is 18, plus 4 is 22, plus 3 is 25. K on 12 equals 0.75. And now we can just multiply both sides by 12. So useful trick for when multiplying decimals by whole numbers is that if you double one, you can halve the other. So if I double that and I halve that, what would I be given? Well, it would become 1.5 times 6, and I can repeat that strategy again, so I can get 3 times 3, and 3 times 3 is 9. So I get 9, 25k equals 9. Divide both sides by 25, and I get 9 on 25 as my k value. However, that is the value of k, and we're all finished, ready to go. Alrighty, so in this probability distribution, for it all to work out, k would have to equal 9 on 25, or 9/25. Alrighty, see you in the next one.